Welcome to Daily Papers, the podcast where we break down fascinating new research. Today, we're diving into the world of brain-computer interfaces.
That's right. Imagine controlling a prosthetic limb or a wheelchair just by thinking about it. That's the long-term goal. But to get there, we first need to get really good at translating brain signals into commands for movement.
And that's exactly what today's paper is about. It's titled Online Decoding of Rat Self-Paced Locomotion Speed from EEG Using Recurrent Neural Networks.
Okay, that's a mouthful. Let's break it down. Decoding just means translating. In this case, translating brain activity into speed. Self-paced locomotion means the animal is choosing how fast to move. It's not being forced on a motorized treadmill.
And EEG stands for electroencephalography. It's a way of listening to the brain's electrical activity, its brainwaves, using electrodes placed on the surface of the skull. It's much less invasive than putting implants deep inside the brain.
So the big question the researchers wanted to answer was, can we accurately figure out how fast a rat is running just by listening to its brainwaves from the outside while it runs at its own pace?
Exactly. The setup involved rats on a special non-motorized treadmill. They had to push the belt themselves. While they were running, walking, or just chilling, the scientists recorded their brain activity from 32 different points all across the cortex.
And they collected a ton of data, over 133 hours of recordings. They then fed all this brainwave data into a type of artificial intelligence called a recurrent neural network, or RNN.
An RNN is a special kind of AI that's really good at understanding sequences of information that unfold over time. Think about how the words in a sentence depend on the words that came before. An RNN is great at that. It's perfect for looking at a continuous stream of brainwaves and finding patterns.
So they trained this AI to look at the stream of EEG data and, moment by moment, predict the exact speed of the treadmill. The big question is, did it work?
It worked spectacularly well. The AI's predictions were incredibly close to the rat's actual running speed. They measured the accuracy using something called a correlation score, where 1 is a perfect match. They got a score of 0.88.
Wow, 0.88 is fantastic. That's like a weather forecast that's right almost 90% of the time. For something as complex as decoding brainwaves in a freely moving animal, that is a huge result.
But here's where it gets really weird and interesting. When the researchers looked at which part of the brain was giving them the most useful information, it wasn't what you'd expect.
You'd think it would be the motor cortex, right? The part of the brain that's directly in charge of sending signals to the muscles to make them move.
That's what everyone would think, but it wasn't. The most predictive signals came from the visual cortex, the part of the brain that processes what the rat is seeing.
That seems backward. Why would the seeing part of the brain be the best predictor for how fast you're running?
The paper suggests that when an animal starts moving, its entire brain shifts into a different state. The visual system, for example, gets heightened and changes its activity patterns, even if the visual input doesn't change. It's like the brain is saying, okay, we're moving now, pay extra attention to the world whizzing by. And that shift in state was the strongest signal the AI could lock onto.
That's incredible. It's not just about the command to run, but the entire brain's experience of running. They also found that the most important brainwaves were the very low-frequency ones, under 8 Hz, kind of like the deep bass line in a song being the key to the whole rhythm.
Totally. And they pushed the experiment even further. They wanted to know if you could train the AI on one rat and then have it work for a totally different rat.
This is a huge deal for practical applications. If you had to spend hours and hours training a BCI for every single person from scratch, it would be a major roadblock.
And what they found was fascinating. The AI decoder worked pretty well across different days for the same rat. The neural signature for running was stable in that one individual. But when they tried to use a decoder trained on rat A for rat B, the performance plummeted. It just didn't work.
So we each have our own unique brain print for movement. My brain signal for walk looks different from your brain signal for walk.
Exactly. It suggests that any future technology will need at least a little bit of personal calibration. But the good news is that a little bit of fine-tuning on the new subject dramatically improved the results. You don't have to start from zero every time.
Okay, there's one more finding from this paper that sounds like it's straight out of science fiction. They didn't just look at the rat's current speed, they tried to use the brainwaves to predict the future.
And it worked. By looking at the brain activity right now, the AI could make a reasonably accurate prediction of what the rat's speed would be a full second later.
A whole second. In brain time, that's an eternity. That means the brainwaves contain information about our intentions before we've even fully acted on them.
And not just the future, the brainwaves also contained a strong memory trace of what the rat was doing up to a second before. It turns out our brains are not just living in the present moment, they are constantly anticipating the future and reflecting on the immediate past.
The implications for prosthetics are mind-boggling. Imagine a prosthetic leg that doesn't just react to your movement, but anticipates it, leading to a much smoother, more natural gait.
So, to sum it all up, this study shows we can decode self-paced, natural movement with incredible accuracy using non-invasive EEG. It revealed the surprising importance of the visual cortex in this process and showed that our neural signatures for movement are highly individual.
And it gave us a peek into how the brain represents the future and past of our actions. It's a foundational piece of work that pushes the dream of advanced mind-controlled assistive devices one big step closer to reality.